Hello friends, so today we are going to solve the questions from modern physics, and these questions are from the year 2022, and we are going to solve 17 questions, and all these 17 questions are from the mains. The advanced version of the 2022 questions we have already completed last time. So the first question, it states that the hydrogen atom from excited state comes to the ground by emitting a photon of wavelength lambda. The wavelength of principal quantum number n of the excited state will be r is the Rydberg constant. So it is given that it comes from a excited state to the ground state. So the value of n will be equal to 1. So you can say that the transition is from excited state to n is equal to 1, which is our ground state. And let us assume that, or rather we can say it is given that the wavelength emitted is lambda. So you can say that our wavelength is our lambda. So let us assume that the excited state is simply represented by n. Therefore, we can write the Rydberg formula and which gives us 1 upon lambda is equal to r 1 upon square minus 1 upon n square. Now we are going to simplify this equation for n, and therefore we can write that our 1 minus 1 upon n square will be equal to 1 upon r times lambda, and from here we can write that 1 upon n square will be equal to 1 minus 1 upon r lambda. And we can take r lambda as LCM. So this will be giving us r lambda minus 1 divided by r lambda. Taking the reciprocal as well as square root, we get a value of n will be equal to r lambda divided by r lambda minus 1 and its square root. So this is the value of n, and option number B is the correct one. Option B is correct. Next question. It states that x upon x plus 4 is the ratio of energy of photons produced due to transition of an electron of a hydrogen atom from its third permitted energy level to the second level and the highest permitted energy level to the second permitted level. So we have to find out value of x. So we have two types of transitions are given to us. In the first part, it is said that is a third to the second, and the second transition it is said to be the highest permissible to the second permitted level. So ratio of energies are given to us. So obviously we are going to start with the equation of the energy of a hydrogen atom for the nth level. So we can say energy for nth level we know is given as E of n, which is equal to minus 13.6 n square electron volt, and the transition is from, in general, let us write that the transition is from initial state Ni to the final state Nf. So based on this, we can write the photon energy so therefore we can write that photon energy, and we can write a formula that our photon energy E photon will be equal to energy at our initial level minus energy at our final level. So we have two transitions. So in the first case, let us assume that the transition is from, or rather we can say it is given that transition is from third to second. So therefore its energy, let us write in the form from third to second, will be equal to energy at third level minus energy at the second level, and this can be written as minus 13.6 upon 3 square, that will be 9, and minus of minus 13.6 upon 2 square, that will be 4. So we get energy during the transition from third to second. We can take, okay, we can write it in a reversal way and take 13.6 as common. So this will be coming as 1 upon 4 minus 1 upon n, 9, sorry, and this will be giving us 1.88 electron volt. And in the second option, it's at the highest permitted level. So obviously the value of n in highest will be infinity. So therefore for second, we can say infinity to the second transition, and energy in this case will be over E infinity to 2, which will be giving us a E infinity minus E of 2. E infinity will be over 0 minus, and E of 2 will be equal to minus 13.6 divided by 4. This will be coming as 3.4 electron volt. And now we are going to find out the ratio. So we can say ratio will be our 1 point, this ratio we will write energy from third to 2, energy from infinity to 2, which will be equal to 1.88 divided by 3.4, and this we can say can be written in the fractional form. Approximately will be equal to 5/9, and this ratio it is given as x plus 4, and we are going to calculate it for x now. So we get this as 9x is equal to 5x plus 20, and this gives us 4x, so x will be equal to 5. So value of x will be equal to 5. Next question. It states that in a hydrogen spectrum, lambda be the wavelength of the first transition line of Lyman series. The wavelength difference will be A alpha between the wavelength of third transition line of the Paschen series and that of second transition line of the Balmer series, where value of A is. So we are supposed to find out value of A, which is being multiplied by the lambda. And in the Lyman series, it states that the wavelength is our lambda when there is a first transition line. Okay. So first transition line means from second to 1. So we can say that first transition in Lyman series, it will be from n is equal to 2, n is equal to 1, and during this transition the wavelength is lambda. Okay. And it says that the difference in wavelength difference between the Paschen series and Balmer series is said to be A lambda. So you can say that wavelength for our Paschen series, and this is in the third transition, minus wavelength in the Balmer series, which is for the second transition. This is given to us as A times lambda, and from here we are going to find out our value of A. So let us understand that with respect to Paschen series, the third transition, and with respect to Balmer series, the second transition. Okay. So we can say that our Paschen series, we are given third transition, so third transition means rather that the value of initial value of n will be equal to 5, and it is going to a final value of 3. And we are having Balmer series. For Balmer series, it is given a second transition, and this second transition, the initial value of n will be over 4, and we having a final value of n will be equal to 2. Now we are going to use the Rydberg formula and divide that as per the given conditions. So we can say Rydberg formula which tells us 1 upon lambda is equal to r times our nf square minus 1 upon ni square. So first is our Lyman series, and the transition is from 2 to 1, and wavelength in that case is our lambda. Therefore we can write that for Lyman series wavelength is lambda, so as it is we can just 1 upon lambda is equal to r, and this comes as final is 1 upon 1 square, and initial is our 2, that is our 2 square. So from here we can write our lambda will be equal to 4 by 3 times r. Similarly, we are going to solve it for Paschen series as well as our Balmer series. Therefore we can say that for our Paschen series, and this gives us 1 upon lambda p and is equal to r, and we have 1 upon 3 square, that is 9, minus 1 upon 5 square, that is 25. So from here we get the wavelength associated with Paschen series. It will be equal to 2 to 5 upon 16 times r. Now we have our finally the Balmer series. 1 upon lambda b will be equal to r, and this will be 1 upon 4 minus 1 upon 16. So this gives us a lambda b will be equal to 16 divided by 3r, and the difference between these two wavelengths is given to us as a lambda. So we simply lambda p minus lambda b, which will be equal to 2 to 5 divided by 16r minus 16 upon 3r, and this will be coming as 419 and 48r, and this is said to given as a lambda, but we also know the equation for lambda. So this comes as a times, and our lambda is our 4 by 3r. So finally we can write this as our a times 4 by 3r will be equal to 419 and 48 times r, and here r and r goes away, and from here we can write the value of a will be equal to 419 multiplied by 3, and this is 4 multiplied by 48. So this will be approximately equal to 6.54. So value of a will be 6.54. Next question. It states that a nucleus of mass m at rest splits into two parts having masses m prime by 3 to m prime by 3, where m prime is less than m. The ratio of de-Broglie wavelength of the two parts will be. And it says that our original is at rest, whose mass is m. Therefore we can just draw an approximate figure for that, and we have a mass m whose initial velocity is equal to 0, and it splits into two parts. So first part is m prime by 3, and we have second part is 2m prime by 3. Its velocity, let us suppose, is v1, and its velocity, let us suppose, our v2. So we can use just conservation of momentum and solve it. So we can say conservation of momentum for this m, let us suppose, is capital P. For this, let us suppose this is P1, and for it, let us suppose P2. So obviously initial momentum will be equal to 0. But according to conservation momentum, we can just write the equation that our P will be equal to P1 plus P2. P is equal to 0. So this gives us that P1 plus P2, which tells that P1 is equal to minus of P2. And this negative, you can say, sign only tells about direction. It means if P1 is moving in upward direction, then P2 will be moving in opposite direction. That is only significance of this. So if we take the magnitude part, therefore we can say that P1 is equal to P2. And we also know that our lambda is equal to our h upon p. So from here we can say that our p is equal to h upon lambda. So we can divide this equation two parts. P1 is equal to h upon lambda 1, P2 is equal to h upon lambda 2. And we need to find out their ratio. Okay, no problem. So we substitute them, we get this as h upon lambda 1 is equal to h upon lambda 2. So here we can say lambda 1 is to lambda 2 is equal to 1 is to 1. So ratio is option C is correct. C is correct. Next question. It states that mass number of two nuclei are in the ratio 4:3. Their nuclear density will be in the ratio of. So this is a straightforward relationship between the mass as well as density. Only we have to keep in mind that we are talking about the nuclear density. Therefore, we start from there. So we can say nuclear density if that is represented as rho will be equal to mass of nucleus and divided by volume of nucleus. And for nucleus, we know that for nucleus, we know that our mass is directly proportional to A, which is our mass number. And radius is proportional to cubic root of our this mass number. And from here we can also write that the volume V will be proportional to cube of the radius, or we can say proportional to our mass number. Therefore, we can write that our density is proportional to, we have mass of nucleus is proportional to A, and volume is also proportional to our A. Therefore, we get this rho will be our constant. That, or indirect, we can also say from here that it will be independent of mass number. Independent of mass number, that is A. Option C is correct. Next question. We are given an electron of mass m with an initial velocity vector v equal to v naught I unit vector enters electric field vector E is equal to minus E naught I unit vector at t is equal to 0. If lambda naught is its de-Broglie wavelength initially, then its de-Broglie wavelength at a time t is. So here we are given a velocity. Let's start with mass is given. So we can say we are given a mass which is of m. We are given velocity which is our initial velocity. And initial velocity is v is equal to v naught I unit vector. So I unit means in positive x direction. And we have electric field. Electric field, it is given as E is equal to minus E naught I unit vector. But here in the question it is mentioned that our E naught is a positive value. Okay, so it means this negative sign indicates that the velocity will be opposite to that of our electric field. Okay. So we can write from here that opposite to velocity direction. Opposite to velocity direction. And we are also given a de-Broglie wavelength. Is lambda naught. Okay. So as soon as the electron enters the electric field, it is going to experience a force. And we can write the formula or equation for that force. So we can say force on electron and that force, let us suppose, is F, will be equal to Q times electric field, and charge is our electron, electric field is our E naught I unit vector. So from here we can say that the force will be equal to E naught I unit vector. And from here we can also say, or as there is a force acting on the electron, so it will be a acceleration also. Therefore we can say that, okay, here also the force will be acting in positive I direction. Therefore from here we can say that our acceleration is in positive x direction, or we can say I unit vector. So we can write that our acceleration A will be equal to force divided by mass. Force is our E naught and mass is m. And we know that if we, in terms of velocity, we can write that, and we can say that, or we can use the kinematics equation also. Suppose the velocity at time t, let me write it here, so you can see using kinematics equation, velocity at time t is equal to initial velocity plus acceleration multiplied by time t. Initial velocity is given to us as v naught. Therefore we can write that velocity at time t is equal to v naught. Acceleration we found out is our e naught m multiplied by t. And now we are supposed to, we are supposed to find out de-Broglie wavelength. So we can say that de-Broglie wavelength, and at a time t, let us call this as lambda t, which will be equal to h divided by momentum at time t, which can be further written as h upon mass velocity at time t. And we are also given that the initial de-Broglie wavelength is lambda naught. So we can say initially we can write that our lambda naught is equal to h upon m times v naught. And therefore we can write that our lambda t will be equal to h, and we have this as mass, substituting equation for this v of t, which is our v naught plus e naught upon m times t. And we can take our mv naught as, or we can say we can factor v naught. So we get this will be equal to over h upon m v naught, and we have this as 1 plus e naught upon m v naught multiplied by t. And this h v naught divided by m v naught is equal to our lambda naught. Therefore we can write that our lambda t will be equal to lambda naught, and we have here 1 plus e naught upon mv0 times T. I think, yeah, this will work. So option A is correct. A is correct. Next question. It states that find the ratio of energies of photons produced due to transition of an electron of hydrogen atom from its second permitted energy level to the first level and highest permitted energy level to the first permitted level. This question we somewhat solved previously also, so this is almost similar, and we can start with our energy for our nth level, which will be equal to minus 13.6 upon n square electron volt, and we are having two transitions. First transition from the second to 1, therefore we can say energy from second to 1 will be equal to E2 minus E1, which can be written as our 13.6 is equal to 1 minus 1 upon 4, and this comes as approximately equal to 10.2 electron volt. And second case, it states from the highest level, which means from infinity to the first, which gives us similarly E infinity to 1 will be equal to energy at infinity minus energy at 1. So this will be 13.16, and this will be our 0 minus E of 1 is our 1. Minus of minus 1, so this will be a plus 1. Okay. So this will be giving us 13.6 electron volt, and just we are going to find out the ratio. Therefore we can say ratio will be equal to energy from second to 1, energy from infinity to 1, which will be 10.2 and 13.6, which will be coming as 3 by 4. So the ratio is our 3 by 4. Next question. It states that light wave traveling in air along x direction is given by E is equal to 540 sine pi 10 raised to power 4 x minus ct. Then the peak value of magnetic field of the wave will be. So here we are supposed to find out only peak value. So peak value of electric field is 540, and the relationship between the two is quite simple. So we can say that our peak value of magnetic field that is B0 will be equal to peak value of electric field divided by speed of light. And so we get this B0 will be equal to E0 is our 540 and C is our 3 into 10 to the power 8. And so we get this will be equal to our 18 into 10 to the power minus 7 Tesla. So option number A is correct. Next question. It states that The magnetic field of a plane EM wave is given by the equation. The amplitude of the electric field will be. So amplitude we can just easily find out by using the formula. The important part is finding out its direction. So the peak value of, or we can say magnitude of magnetic field is our 2 into 10 to the power 8. So we can say that our electric field E naught will be equal to C times B naught. So we get from here that our E naught is equal to C is our speed of light, 3 into 10 to the power 8, and B naught is 2 into 10 to the power minus 8. So this gives us 6 volt per meter. So only possibility is that option A or option C with respect to direction. And from the given equation we can say that our magnetic field direction of magnetic field is our J unit vector, or we can say in Y direction. And we know that our electric field is perpendicular to the magnetic field and the wave vector is perpendicular. So all these are mutually perpendicular to with each other, okay, and they satisfy, you can say, the right hand rule, which states that wave vector cross E will be giving us a magnetic field multiplied by the angular frequency. Okay. So we need to find out this because electric field, one second, we need to find out the wave vector k, okay, because direction of B we already know is along J unit vector or Y direction. So from the given equation we are going to take the argument of sine wave, you can say argument of sine, and that argument is giving us 0.5 into 10 to the power 3, 0.5 into 10 to the power 3 times x plus 1.5 into 10 to the power 11 times t. So if we see this format is our kx plus omega t. Therefore we can write that the wave is traveling in negative x direction. Okay. Because the standard format for this kx plus omega t, this standard format is, the comparison with which we make is kx minus of omega t. Okay. Thus we can say that our this wave vector k will be our minus of I. Now we can just find out the our electric field. So we have our K. We know that our magnetic field is our J unit vector. K is along minus I unit vector. Therefore, our electric field will be in E naught, and we are going to have a K unit vector that is in Z direction. So option C is correct. Next question. It states that the oscillating magnetic field in a plane EM wave is given by B of phi is 5 into 10 to the power minus 6 sine of 1000 pi 5x minus 4 times 10 to the power 8 t Tesla. The amplitude of electric field. So this is directly based on the simple formula. We can say that our but in this case in general, let me first of all write, we can say that our electric field its magnitude over E naught will be equal to V times B naught, and V is the velocity of that EM wave in any medium. If the medium is vacuum, that value of V is equal to C, or we can just find out value of V for a particular medium. So for our velocity V, which is our velocity of EM wave, this will be equal to our 4 into 10 to the power 8 and divide by 5. Okay, that is our, this is our kx minus omega t, and this will be coming as 8 into 10 to the power 7. Therefore, our E naught will be equal to 8 into 10 to the power 7, and our B naught is our 5 into 10 to the power minus 6. 5 into 10 to the power minus 6, and this comes as our 4 into 10 to the power 2 volt per meter. So option D is correct. Next question. We are given that the disintegration rate of a certain radioactive sample at any instant is 4250 disintegration per minute. 10 minutes later, the rate becomes 2250 disintegration per minute. The approximate decay constant is. So here we are going to find out decay constant, and for that we can just use our radioactive decay law. You can say that our radioactive decay law, which gives us that R is equal to R naught e raised to power minus lambda t, where lambda is our decay constant. So we can write this will be equal to our R upon R naught and is equal to e raised to power minus lambda t, And if we take natural log of both sides, so we get natural log of r upon r naught is equal to minus lambda t. And we are given that our initial disintegration is 40 to 50. So we can write our initial decay rate is our r naught, which is our 4250 disintegration per minute, and after time t, at time t is equal to 10 minutes, the decay rate, that is value of r, comes as 2250. So we simply substitute the values, and we can write that our natural log of r is our 2250, r naught is 4250, is equal to minus lambda t is our 10. So from here we get minus lambda 10 minus 10 lambda will be equal to minus natural log of 1.88, and this will be giving us minus 10 lambda will be equal to minus of 0.63, giving us that the value of lambda will be equal to 0.063 per minute. So option number C is correct. Next question. It states that two lighter nuclei combine to form a comparatively heavier nucleus by the relation that is x plus x gives us a y. The binding energy per nucleon for our x and y are given as 1.1 and 7.6 mega electron volt respectively. The energy released in this process is so in this case we are going to use our mass defect, and from there we can just find out our, or we can also use the binding energy, because the binding energy is given directly to us and the difference will be giving us a energy released. So the given reaction is our, that we are having x plus x, it is giving us a y, and so let us find out the total binding energy, because the binding energy is given to us as a per nucleon. So we can say that the total binding energy so we have two x nuclei for 2x nuclei, which can be written as 2 multiplied by mass number of x multiplied by binding energy per nucleus of x. Binding energy per nucleons of X, and you can write this will be equal to our 2 multiplied by 2 multiplied by 1.1, which gives us 4.4 mega electron volt. Similarly for our Y also. For Y, which will be equal to, because a product is single, so it will be only mass number of Y multiplied by binding energy per nucleon of Y. And this will be equal to 4 into 7.6, giving us 30.4 mega electron volt. So energy released that is our Q will be equal to binding energy of reactants, binding energy of product minus binding energy of reactant. And substitute the values. Reactant product is our Y, so that is 30.4. Reactant is our X, which is 4.4, which gives us the value of Q is equal to 26.0 mega electron volt. So it is 26. Next question. It states that what is the half-life period of a radioactive material if its activity drops to 1/16th of the initial value of 30 years? So in this case, the comparative that is taken is with respect to the initial value. So let us assume that the initial value is A0. Initial value is A0, and it states that after time is equal to 30 years, after t is equal to 30 years, let us suppose the activity is given as A, so this A will be equal to 1/16 times A0. Now we can just use our the formula for the decay law for activity. Decay law for activity, which gives us that A is equal to A0 1/2, and this comes our T upon T half, and we have to suppose to find out the T half, that is half-life. So we can write this as A upon A0, which will equal to 1/16 is equal to 1/2, and small t is our 30 years. This becomes 30 upon T half, and this can be written as 1/2 whole raised to power 4 is equal to 1/2 and this is our 30 upon T half. Therefore, we can say that our 30 upon T half is equal to 4, which gives us that T half is equal to 30 upon 4 will be equal to 7.5 years. Next question. It states that the activity of a radioactive material is 6.4 into 10 to the power minus 4 curie. Its half-life is 5 days. The activity will become 5 into 10 to the power 6 curie after. Same question, but after asking a little bit different way, and here we have to find out the value of T. So here we are given initial activity. Initial activity A naught is our 6.4 into 10 to the power minus 4, and we are also given T half-life, which is our 5 days. Final activity is also given to us. Final activity, that is value of A is our 5 into 10 to the power minus 4. So once again, we are going to use decay law. And it tells us that our A is equal to A naught half T upon T half. And we are supposed to find out this value of T. We simply substitute all the values. A is given to us as 5 into 10 to the power minus 4 divided by A naught is 6.4 into 10 to the power minus 4 is equal to 1 by 2, and half-life is given as 5 days. So we can write this will be equal to our 1 upon 1 to 8 is equal to 1 upon 2, and this comes as T upon 5, and which will be equal to 1 upon 28 can be written as 1 upon 2 whole raised to power 7. So we get T upon 5 is equal to 7, giving us T is equal to 35 days. And option number D is correct. Next question. It states that a freshly prepared radioactive source of half-life 2 hours 30 minutes emits radiation which is 64 times the permissible safe level. The minimum time after which it would be possible to work safely with the source will be hours. So we are given that T half-life is given to us. So we can say T half is our 2 hours and 30 minutes, and initial radiation level is 64 times the safe level. So we can see initial level is 64 times safe level, and we have to find out time T. we want that find T under the condition that the radiation level is less than equal to safe level. So we can use the decay formula for activity, or in other term we can also call it as a radiation level. So we can say decay formula for radiation level. And which will be equal to over I is equal to I naught half whole raised power T, and this is over T half. And this can be written as I upon I naught is equal to half T upon T half, and I upon I naught, initial level is we know is our I naught, and safe level is suppose our I, sorry, one second, yeah, and multiply by 64. So I upon I naught will be equal to 1 upon 64, and this is quite straightforward now. So we can write our 1 upon 2 whole raised power 6 is equal to 1 upon 2, and this T half is given as 2 hour 30 minutes. So this comes as T upon 2.5, giving us T upon 2.5 is equal to 6, which gives us that the value of T will be equal to 15 hours. So we have this option as 15 hours. Next question. It states that a radioactive sample decays 7 by 8 times its original quantity in 15 minutes. The half-life of sample is. So let us assume that the initial quantity or original quantity is N naught. Let us call that initial quantity, or we can also call it as an original quantity. Is, let us suppose, is our N naught, and is that it decays 7 upon 8 times the original quantity. So from here we can say that amount remaining after decaying, or we can say quantity remaining after decaying. Quantity after decay. Let us suppose that is of N, which will be equal to initial quantity minus 7 upon 8 times initial quantity. So this gives us that quantity is equal to 1 by 8 times N naught. Now we can use the decay formula. Decay formula, it gives us that N is equal to N naught 1 by 2 T upon T half. Half-life we are going to find out, and value of T is given to us 15. And from here we can write that N upon N naught is equal to 1 upon 8. So we get N upon N naught is equal to 1 upon 2, and it is given as 15 minutes divided by T half, and this is our 1 upon 8 is equal to 1 upon 2 15 upon T half, and 1 upon 8 can be written as 1 upon 2 whole raised to power 3. So we get from here that 15 upon T half is equal to 3, and therefore our T half is equal to 5 minutes. So option number A is correct. A is correct. Next question. It states that two radioactive materials A and B have a decay constant 25 lambda and 16 lambda respectively. Initially they have same number of nuclei, then the ratio of number of nuclei of B to A to that of A will be E after time 1 upon A lambda. We have to find out value of A. So we have two materials A and B and their respective decay constant. Therefore we can write that decay constant for A is our 25 lambda and decay constant for B is our 16 lambda, and it states that initially they have same number of nuclei. You can say that initially they have same number of nuclei, which can be written as that Na naught is equal to Nb naught, and let us suppose this is our N naught, and after time 1 upon A lambda, after time t is equal to 1 upon A lambda, ratio of Nb to Na is said to be given as E. So we can use our decay formula. Which tells us that N is equal to N naught e raised to power minus lambda t. So we have two substances. We can divide this formula to two parts. We can write our Na will be equal to Na naught e raised to power minus 25 lambda multiplied by t, and we have this is Nb is equal to our Nb naught e raised to power minus 16 lambda t. We take the ratio Nb upon Na is equal to Nb naught e raised to power minus 16 lambda times t, Na naught e raised to power minus 25 lambda t, and this Nb naught Na naught are same, so we get this will be e raised to power 16 minus of 16 plus of 25, giving us 9 lambda t, and this ratio is said to be equal to our E. Therefore our e raised to power 1. So we get that our 9 lambda t is equal to 1, giving us 9 lambda t is equal to 1 upon 9 lambda t is equal to 1, 9 lambda t is equal to 1 upon 9 lambda t is equal to 1, 9 lambda t is equal to 1 upon 9 lambda t is equal to 1, 9 lambda t is equal to 1 upon 9 lambda t is equal to 1, 9 lambda t is equal to 1 upon 9 lambda t is equal to 1, 9 lambda t is equal to 1 upon 9 lambda t is equal to 1, 9 lambda t is equal to 1 upon 9 lambda t is equal to 1, 9 lambda t is equal to 1 upon 9 lambda t is equal to 1, 9 lambda t is equal to 1 upon 9 lambda t is equal to 1, 9 lambda t is equal to 1 upon 9 lambda t is equal to 1, 9 lambda t is equal to 1 upon 9 lambda t is equal to 1, 9 lambda t is equal to 1 upon 9 1 second. Yeah, so T is given to us as 1 upon A lambda. So we substitute it, 9 lambda into 1 upon A lambda is equal to 1, which gives us that the value of A is equal to 9. So value of A is equal to 9. So this completes all the questions for the year 2022 mains. Total 17 questions we solved in this part. So this completes all the 17 questions for the year 2022. Thank you.